Hello everyone. Today we are going to study second chapter, work and energy, and the topics are kinetic energy and work energy theorem. We just review the first chapter, the main topics of the first chapter. The first topic is motion and its types. When an object changes its position with time, it is said that object is in motion. There are various types of motion such as rectilinear motion, oscillatory motion, curvilinear motion, periodic motion, uniform motion and non-uniform motion. Displacement, velocity and acceleration. These three are interrelated with each other. Displacement is the change in object position. Velocity is the rate of change of displacement and acceleration is the rate of change of velocity. Equations of motion. The first equation of motion is V is equal to U plus AT. Second equation is V is equal to UT plus 1/2 AT square. And third is V square is equal to U square plus 2AX. Where U is initial velocity, V is final velocity, A is acceleration, T is time taken, and X is displacement. Then Newton's laws of motion. Newton's first law states that every inanimate body continues in its state of rest or of uniform motion in a straight line unless it is acted upon by some external force to change that state. Or simply, we can say that when no force acts on a body, the acceleration of the body is zero. Similarly, Newton's second law of motion states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. And third law states that to every action there is always equal and opposite reaction. Fundamental forces in nature. There are four fundamental forces in nature: gravitational force, electromagnetic force, strong interaction force and weak interaction force. Then pseudo force. It is also called as a fictitious force. It is a fake force which is arise in a non-inertial frame due to acceleration of the frames. Then frame of reference. There are two types of frame of reference: inertial and non-inertial. So let us start second chapter, work and energy. The content of this chapter: kinetic energy. It is due to motion of an object. Then work energy theorem, which gives the relation between work and energy. That is, W is equal to change in kinetic energies. Then work done by a constant force and work done by a varying force. Conservative force and non-conservative force. So, potential energy, then law of conservation of mechanical energy, and we also solve the problems. Introduction. In this chapter, we shall study the energy acquired by a body by considering a related concept, that is work. In physics, we use the term work to describe the process of transferring energy from one object to another or converting energy from one form to other form. So, work is nothing but a transfer of energy. The work is said to be done on an object if a force acting on an object is able to move the object through some distance in the direction of force. When work is done on an object, then object acquires the ability to do work. Means when an applied force moves an object through a displacement, then work is done on an object. For example, when you throw a ball, then you do work on the ball to give it speed. As it leaves your hand, when the moving ball hits on some other body, it applies a force on that body, due to which it gets displaced. Thus, work is done by a ball. Then kinetic energy. It is the energy due to motion. Work energy theorem. Work done by a constant force, which is defined as the product of the force and displacement in the direction of force. As we know that the capacity to do work is called as energy, which appears in various forms such as mechanical energy, light energy, sound energy, electric energy, and heat energy. In mechanics, we are concerned with mechanical energy, which is of two types, namely kinetic energy and potential energy. And mechanical energy is the sum of kinetic energy and potential energy. So let us study kinetic energy. Kinetic means the movement. The word kinetic means movement, or kinetic energy is the energy of motion. If an object is moving, it is said that that object have a kinetic energy. It is defined as the ability to do work on the object, or the energy possessed by a body by the virtue of its motion is called kinetic energy. Kinetic energy is a scalar quantity and is measured in the same units as work done. That means its SI unit is joule and CGS unit is erg. The kinetic energy of a particle depends on its velocity. The velocity of the particle can be changed by applying a force which can do work on the particle. Hence, kinetic energy of a particle can be changed by applying a force. If m is mass of the particle and is moving with velocity v, by applying force, then kinetic energy K is equal to 1/2 m into v square. In vector form, this v square can be written as vector v dot vector v, means K is equal to 1/2 m vector v dot vector v. Differentiating this equation with respect to t, we get dk by dt is equal to vector v dot m into d dt of vector v by using product formula. Using Newton's second law of motion, that is F is equal to ma, and where a is acceleration, and in terms of velocity, acceleration is nothing but rate of change of velocity. So we can write F is equal to m into d by dt of vector v. Hence, above equation may be written as dk by dt is equal to vector v dot vector f, which is equal to v of cos theta, where theta is angle between vector f and vector v. F cos theta is equal to ft, which is a tangential force. Then above equation becomes dk by dt, which is equal to ft into v. From this equation, it is clear that kinetic energy of a body changes if speed of the particle changes when force acting on the particle has tangential component, that is F cos theta. If force acting on the particle is perpendicular to the direction of velocity, means theta is equal to 90 degree, then kinetic energy of the particle does not change. As we know that dk by dt is equal to ft into v, or dk is equal to ft into v dt, when f is perpendicular to v, then cos theta is equal to 0, because if f is perpendicular to v, then angle between them is 90 degree and cos 90 is 0, means cos theta is equal to 0. Therefore, work done, which is equal to vector f dot vector ds, which is equal to f ds cos theta, is 0. Hence, dk is equal to vector f dot vector v dt is equal to 0. K is constant, so kinetic energy does not change. These are the examples of kinetic energy. All objects are in motion, so they have kinetic energy. About kinetic energy, interesting things are kinetic energy of an object depends on two variables, that are the velocity v of an object, mass m, that is how much matter is in the object. Kinetic energy directly proportional to the square of velocity of an object. It does not depend on direction, as it is a scalar quantity and it is always positive. So this picture shows the motion of an object. Faster the object moves, more kinetic energy is produced, or the greater the mass and speed of an object, there will be more kinetic energy. In this diagram, we have to ask a question: when following objects move with same speed, which object will have more kinetic energy? And the answer is, truck has more mass, therefore it has more kinetic energy. According to the relation, K is equal to 1/2 m into v square. Then work done, Work can be expressed as work done on a body or work done by a body. Work is said to be done if a force acting on a body is able to move it through some distance in the direction of the force. It is the product of magnitude of the force and the displacement through which the body moves in the direction of force. Or work done is equal to force into displacement. Mathematically, if dW is the work done, F is applied force and ds be the displacement in the direction of force, then we can write dW is equal to F ds. There are many examples where the force is applied on the body but the work done by the force is 0. Figure shows that when a person pushes the wall by applying a force on the wall, then wall does not move, means no work is done on the wall. Means displacement is 0 in the direction of force, then no work is done or work done by the force is 0. Unit and dimensions of work done. The SI unit of work done or work is joule and CGS unit is erg. As we know that W is equal to Fs, that is work done is the product of force into displacement, means 1 joule is equal to 1 Newton into 1 meter or 1 joule is equal to 1 Newton meter. Thus, work done by the force is said to be 1 joule if a force of 1 Newton displaces a body through 1 meter in the direction of force. Then dimensions. From the above equation, that is W is equal to Fs, as we know the dimensions of force and dimensions of displacement, then we can calculate dimensions of work done. So W is equal to dimensions of force m1, L1, t minus 2. Similarly, dimensions of displacement m0, L1, t0, which is equal to dimensions of work done m1, L2, t minus 2. Work energy theorem. This gives the relationship between work and energy, means work and kinetic energy. The work energy theorem states that the work done by a force acting on a body equals the change in the particle's kinetic energy. Mathematically, we can write W is equal to Kf minus Ki or delta Ke. Kf is the final kinetic energy and Ki is initial kinetic energy. As W is equal to 1/2 m into v square minus 1/2 m into u square, which is equal to delta K. U is initial velocity and v is final velocity of the particle. The work energy theorem can be derived from Newton's second law, that is F is equal to ma. Means from this relation we can say that work transfers energy from one place to another or one form to another form. Then we can prove the work energy theorem. For that, we have to consider a body of mass m and a constant force F is applied on the body. So body displaces through distance ds in a time dt in the direction of force. As the displacement is in the direction of applied force, then angle between F and ds is 0. Means theta is 0. Therefore cos theta is 1. The work done by the force is dw is equal to vector F dot vector ds. And dot product of two vector is F ds cos theta. As angle between vector F and vector ds is 0, therefore our equation becomes dw is equal to F ds. According to Newton's second law of motion, F is equal to ma, or F is equal to m into dv by dt. As we know that a, that is acceleration, is nothing but rate of change of velocity. Hence dw is equal to f ds, which is equal to m into a into ds. Or m into dv by dt into ds. By putting value of a here, that is dv by dt, so we get m dv by dt into ds. Or m into, rearrange this equation, we get m dv into ds by dt. And as s is displacement, therefore rate of change of displacement is velocity. So dw is equal to m dv into v. If the force applied increases the velocity from initial velocity u to final velocity v, then the total work done on a body is v is equal to integration of u to v m v into dv. Means integrate above equation. Or as m is constant, that is mass of a body, so we get w is equal to m integration u to v v dv, and integration of v with respect to dv is v square by 2. So we get 1/2 m v square minus 1/2 m u square. That is equal to kf minus ki, where kf is equal to 1/2 m v square and ki is equal to 1/2 m u square. Hence, work done on the body is equal to the change in its kinetic energy. So this is about work energy theorem. Then next one is work done with a constant force. If a force F acting on the body displaces the body through small displacement ds in the direction of force, then dw is equal to magnitude of vector F into magnitude of vector ds, which is equal to f ds. Means the work done during the finite displacement s in the direction of force F is w is equal to integration of f ds. As f is constant during the displacement s, then work done w is equal to f integration ds, and integration of ds is s, therefore w is equal to fs, as shown in figure. A constant force is applied to a body. ds is the small displacement and S is a finite displacement in the direction of force F. At that time we get W is equal to Fs. F is constant force acting on the body. ds is the small displacement in the direction of force, and S is the finite displacement which is also in the direction of force. But if a constant force F along a direction making an angle theta with the direction of displacement ds, then the work done by a constant force is obtained by resolving the force F into two rectangular components. Figure shows that a constant force F is applied so that it makes an angle theta with the direction of displacement, means along x-axis. So by resolving force F, the two magnitudes of the two components are Fx, which is along direction of ds, means along x-axis is Fx is equal to f cos theta, and second one is Fy along the direction perpendicular to ds, means along y-axis, Fy is equal to f sin theta. But body does not move along y-axis or along the component of force Fy, then Fy does no work on the body. The work done by the component Fx is dW is equal to Fx dx, means we only consider the x component because displacement is along x-axis. But Fx is equal to f cos theta. Therefore, dW is equal to f cos theta into ds or f ds cos theta. And this f ds cos theta can be written as vector f dot vector ds. So, the work done during a finite displacement is W is equal to integration of vector f dot vector ds, means vector f, as f is constant, so vector f integration vector ds, and integration of ds is s, so we get vector f dot vector s or fs cos theta. Thus, work done by constant force is defined as the dot product of applied force and the displacement produced by the force. Or from this equation, we also say that the amount of work done by a constant force depends only on the end position and not on the intermediate path. And the work done in a round trip is always 0. The work done in a round trip is always 0. From this equation, W is equal to Fs cos theta. This work done may be positive, negative or 0. Let us consider these three cases. First case is work done may be positive. If vector f and vector s are in same direction, then W is equal to Fs. Then we can say that the work done is positive. As vector F and S are in same direction, means angle between them is 0, and from the relation W is equal to Fs cos theta, means cos theta is 0 and cos 0 is 1. Therefore, we get W is equal to Fs, which is shown in the diagram. This is direction of force and this is direction of displacement, means both are in same direction, that is theta is equal to 0 degree. And its example of positive work done is when a body falls freely under gravitational force, then work done by the gravitational force is positive. If vector F and vector S are perpendicular to each other, then W is equal to 0, that is work done is 0. As vector F and S are perpendicular, means angle between them is 90 degree, and according to the relation W is equal to Fs cos theta or Fs cos 90 and cos 90 is 0, therefore we get W is equal to 0, which is shown in the figure. This is direction of force F perpendicular to S, therefore theta is equal to 90 degree. And the example is when coolie moves on a railway platform with load on his head, then work done by the coolie is 0. And another example is pushing the wall by a person. At that time, wall does not move, means work done is 0. Then third case is if force F and displacement are in opposite direction, then W is equal to minus Fs, means work done is negative. As F and S are in opposite direction, means angle between them is 180 degree or pi. So by the relation W is equal to Fs cos theta or Fs cos pi, value of cos pi is minus 1. So we get W is equal to minus Fs. This is direction of force F and S is in opposite direction. So theta will be 180 degree. And the example is the work done by the frictional force when we push the book to a distance. Thank you.